Now, a few things about OpenHydroQual. First of all, OpenHydroQual is not specifically for LIDs. You can actually use it to model a wide range of water systems, from open channel systems, flow in unsaturated soil, rainfall runoff, that's obvious, sewer systems, groundwater, smart control systems, water quality, reactors, for example, in water treatment plants and so on, sedimentation for water treatment processes. I'll show you the list of plugins that it has. So it's highly flexible. So it's basically based on some plugins. All the governing equations are defined outside of the code. None of them are hard-coded. You can see the governing equations. They are in some JSON files that you can find. You can alter them if you want. You can make your own components based on your own governing equations and things like that. So it's completely transparent, and I'll show you how basically you can actually see the equations that are used if you're interested. Then, as I said, it's extensible in the sense that, people have had some specific, uses, applications, so they needed a certain type of component to be used, and they just made it themselves. And I'll be happy to work with you if you contact to, go around how to do basically implement things. Today I'm not gonna go over, how to define or build new components and things like that. I'm just going to talk about the use. But if you're interested, there are some resources out there that you can use. So essentially, the tool was built around these three principles: flexibility, transparency, and extensibility. So it basically said living, breathing kind of modeling system. It's, if you check the download page, you'll see that every month or so I basically update it. Or it can also be crowdsourced, so people can actually build components and then it can be added to the system. Okay, why is it not moving? Okay, so since I thought, some of you may be familiar with SWMM because it's an LID conference, just some comparisons with EPA SWMM. Of course, SWMM is perfect for modeling sewer networks. Okay, it actually has some advantages, but then in terms of certain things, in terms of flexibility, SWMM basically defines certain components. You have nodes and pipes and so on, maybe LIDs and so forth. In OpenHydroQual, you actually assemble your system, so you can actually build your. Let's say you have a stormwater control measure. You want to configure it in a certain way, or you're representing in a certain way, in your way. So you're more interested in, let's say, I don't know, what's the infiltration into native soil. So you want to actually model that in a kind of more detail, right? Or you're interested in a particular. So basically, it gives you a lot of flexibility in that sense. If you want to see the governing equations in SWMM, of course, you can go to the user's manual. But if you want to actually see them, you have to go to the C code and see how they are implemented. In OpenHydroQual, they're just available. You can just go and see them as text files, basically, JSON files. In OpenHydroQual, you can add new blocks, links, reactions, or types of them. And I'll tell you what I mean by blocks and links shortly. So you can actually add them. Now, in terms of the physics, for example, for subsurface flow, or infiltration, SWMM uses simplified infiltration, green amp, Horton, or curve number. In OpenHydroQual, you can use those things, you can implement those things, but the default is actually recharge equation with Wangen-Eckern model. For water quality, you have build up and wash off in SWMM, but then all you can do, as far as I know, is you can actually assign a decay factor, and then you just get the removal. In OpenHydroQual, you can do multi-component reactive transport. So let's say, for example, you're interested in nitrogen removal to do denitrification. The nitrogen removal depends on oxygen level. So oxygen is an inhibiting factor, so you want to have low oxygen concentration. And then it depends on carbon availability, and then nitrate itself. So it's actually a multi-component process. You can model those processes in OpenHydroQual. and I'll tell you how to do that. Then OpenHydroQual has built-in inverse modeling or parameter estimation capability, both deterministic parameter estimation that uses genetic algorithm to minimize the difference between any observed data that you specify and your model results, or probabilistically using Bayesian and Markov chain Monte Carlo, which is sort of advanced. But anyways, the Bayesian one will give you, instead of giving you a single value for the parameters, it'll give you probability distributions, basically. So if you want to do, I don't know, risk assessment or things like that, you can then use that to do it. Nothing against SWM. I actually use SWM myself, but I just wanted to give you some differentiations. So I think I covered most of these things, so I'm going to actually skip this slide. So basically, it's just some basics. So a model, in OpenHydroQual, a model is made of mainly three things. Something that I call blocks in this course. We can also say nodes or blocks. So these are things that you do mass balancing. So basically, we actually solve the mass balance equation in blocks, right? And then you have these things called links. Links are things that you use to connect the blocks to each other. Basically, they represent the fluxes, right? The fluxes between the blocks. So you can have, for example, you can represent your soil as multiple layers, and then there's an interface between them. That's a link, and the link determines how much flow, for example, goes from one soil layer to another one, or how much mass of certain chemical goes from one to the other one, right? So each nodes and links, they all have equations. Essentially, nodes have equations that ultimately should determine the hydraulic head based on the storage, right? But you can have blocks representing, I don't know, soil, pond, a segment of a channel, groundwater, and all those things. And then the links are the connectivity between them. And then you have sources too. Sources are things that add or deduct things from the mass balance. So for example, rainfall is considered a source. You can have evapotranspiration, even though it's not a source of sink, but it's just classified under source. The things that the value is negative. You can have, I don't know, loading of a certain chemical or pollutants and things like that as a source. And then we also have several other things, constituents. So basically, if you want to do water quality and you have water quality constituents, that's what it is. You define them. Constituents can be mobile. They can actually move to the system. They can also be immobile, right? So basically, I don't know, for example, it's something that is sorbed to your solid phase, or something that is, I don't know, immobile particles are deposited at the bottom of your channel and so forth. You have reactions. They're transformations, right? They can be, chemical reactions, but in our area, it's usually, a lot of times they're like microbially mediated reactions. So things that are done through microbes. You have parameters. So what it is the parameters are used for parameter estimation. So I can say, for example, I don't know. So let's say you want to calibrate, or you're building a model. You don't know what the hydraulic conductivity is. You want to do some, calibration or parameter estimation. What you can do is I can say, I define this parameter called saturated hydraulic conductivity, for example, and I assign it to these properties of these soils. And then you use that to, for example, do, I don't know, model calibration and things like that. To do calibration or parameter estimation, we also need some observations. So observation can represent any output. So I can say my flow out of the, I don't know, my weir or whatever. The flow here is that's something that I measured, or the head here was something that I measured, or water depth here was something that I measured, or a combination of them, right? And then also, I mentioned about parameter calibration. OpenHydroQual can also do optimization. So you can actually define objective functions. Let's say you want to design your LID, I don't know, to meet certain criteria, to, for example, minimize your, I don't know, peak flow, or your flow exceedance from for a certain exceedance probability and things like that. You can define that as an objective function and then use the parameters and say, okay, what should be the value of, for example, this parameter's value can be, I don't know, the height of your riser or something. And you would say, okay, what should be the riser height to achieve that goal or to minimize this thing, right? I'm not gonna, I don't think we have time to go over inverse modeling and optimization, but there are resources out there. If you send me an email, there are some resources that I can show you and show you how to do this. I already explained, blocks and links, what they are. Okay, so this is the thing. I can go to my computer, or you guys can go to your computer to this folder in program files, OpenHydroQual. There's a subfolder called resources. There's a bunch of JSON files, and those JSON files, they define these things that we call plugins. So a plugin is just a collection of components. So for example, there's a plugin for soil, unsaturated soil. It includes soil blocks, links between soils, and then some other components. So each plugin contains multiple components, not just one. You can see the equations, and then it's, I know it's hard to read this, but this is the way it looks like. So basically, it's a JSON file. I don't know if you're familiar with JSON. It's pretty straightforward data structure. So what it says is that each component, let's say I have soil, for example, a soil block, something that represents soil, what kind of properties it has, okay? The properties can be something that is fixed. Let's say the depth of my soil layer, the area of my soil block, okay? Or they can be time series. For example, I don't know, inflow into my soil, if I have inflow, right? Or if I have it can be a source. For example, I have precipitation going to my soil, right? They can be strings sometimes, it can be Boolean and so forth, right? And then here we define whether you want to see them in your output or you don't want to see them in your output, or what are units, right? By the way, OpenHydroQual allows different units, so you can actually use different units in your system. Actually, not necessarily the same system of unit. You can actually build a model that you define some of the things using feet and some other things using meters. Anyways, and links. So that's what it is. So now that was my background about OpenHydroQual. What I'm going to now is that I'll start just showing you how it works. Okay. So I'm going to start from a very simple model, and then I'm going to move to. I'm going to make it more complex, right? So I'm going to actually use the same thing and then add some things to it. So basically, what I'm going to do is that I'm going to start from a detention basin with a predefined inflow. Okay. No, actually not a predefined. That's probably not a very accurate title. So with a design storm. So I'm going to actually still have a watershed, and then I'm going to rain on the watershed and so forth, and so on. But anyways, so basically this is what I'm going to build as the first step. We have a catchment. We have a detention pond. The detention pond, initially I will make it have just overflow. So let's say I know what I always get confused between detention and retention pond, but I think one of them that has underdrain is called what? Retention pond, and then the one that doesn't have is called detention pond, but I can be wrong. Anyways, so I'm going to add a weir, and then it's going to go to a sewer pipe, right? So that's the simplest thing I'm going to start from. So here's what we're going to do. We need a contributing subcatchment. So at this time, I'm not going to consider any infiltration, any evaporation from the pond. So we have a contributing subcatchment. What the subcatchment does is it converts runoff, convert the rainfall into runoff using slope, width, and Manning's roughness coefficient. This is based on kinematic wave. So the one that I make is based on kinematic wave equation. But you can actually, there are other alternatives that use other routing models. Then my pond. So basically for the pond, what we need is that we need a relationship between the storage and the water depth, okay? Because of the bathymetry of the pond, that the relationship between the storage and the water depth is nonlinear. Typically what people do is that they represent it using a kind of power law sort of equation. So basically storage is a coefficient times the water depth to some power, right? Then water level evolves by mass balance, obviously. Then I'm going to have an overflow weir. It's activated when the pond water level exceeds some crest elevation. I'm gonna use a rating curve like this. By the way, something the default units are, the length units are always in meters. The time units are days. That's what happens inside the code. So basically, whatever you can use your information with any unit system that you want. What it does is that it converts them to metric, not exactly metric, because the time is in metric, time is in seconds, but the time in here is in days, right? It converts them to that, and it solves the equation based on that, and then it give you back the results. You can then convert the results to any unit system that you want to, right? But then any time in doubt, anytime the unit is here, it's a tricky thing, because this alpha has a kind of the unit is not very, I mean, first of all, it depends on this exponent, right? So the unit is kind of weird, odd. So basically, this is one of the cases. So whenever you're in doubt, assume that everything is in, the lengths are in meters, the times are in day. So if you want to determine that, use it based on that. Anyhow. Okay. Then what I'm going to do is that, so I have a sewer pipe, but let's say I'm going to model sewer pipe in this course too. But at this time, let's say I don't care about what happens to my water when it just goes out in the sewer pipe. So as soon as it gets out of my system, it's gone. I don't care about what happens afterward. If I want to do that, then I can actually consider this my boundary condition, which means I'm going to use this thing called a fixed head boundary. So a fixed head boundary is something that its storage can change, but its head does not change. So it's like a large body of receiving water. I don't know, if you discharge into a lake or an ocean, it probably can be represented as a fixed head boundary, because its head is not significantly affected by how much water you discharge in it. Okay, so let's get it started. These are the parameters that I'm going to use to build the model. I have tried them and I've saved them on my machine. In fact, I shared a Dropbox folder with you guys. If you have downloaded it, downloaded data or something, it's the things that I'm creating are saved there too. Basically, it's the files are called named stage 1, stage 2, stage 3, and so on. If you go and open them, you'll see them, right? So basically, I just tested and saved things there. I wanted to give myself a little protection too, in case I mess up things. I can always go and load those things. Anyways, so basically, these are the parameters I'm gonna go with. So let's say I have a catchment drainage area 2 hectares. That's 20,000 square meters. You need a flow length, flow width, just like whenever you want to do rainfall runoff modeling on a impervious catchment. There's an average slope of, let's say, 1%, Manning roughness coefficient, and then there's a runoff coefficient of 0.8. Then we have a pond. These are the numbers that I'm going to use for the storage depth relationship for the pond. So alpha is going to be 500, beta is going to be 2. Not sure if that unit is correct. Let's see. Yes, it happens to be, it is, right? So anyways, and then we have a weir. We're going to assume a sharp-crested rectangular weir. If you do the calculation using equations for sharp-crested, rectangular weirs, and basically you'll get an alpha value. So when there's a crest elevation 1.2, weir length 2, and so forth, and then beta is going to be 1.5. The flow units, as I said, is going to be cubic meters per day, even though you can get your results in other units. And then the receiving water, as I said, it's going to be a fixed head boundary. I'm going to assume a constant head of 0.1 above the pond bottom. And then I'm going to do this. I'm going to use the design storm first, and then I'm going to do long-term simulation, right? So you can do design storm or that. So let's get started. I need to go back and forth between this slide and then OpenHydroQual window because I can't really memorize all these numbers. But anyways, I'll try to memorize some so that reduces my. So anyways, I mean, first, you know how to start OpenHydroQual. So when you start OpenHydroQual, you're going to get this blank window. Let me tell you a few things. So actually, look, if you look at here, it says there's some toolbars: blocks, links, sources, constituents, objective functions, observations, parameters, reactions, and so on, and reaction parameters. What they are the same classes of types that I just earlier talked about. So now, by default, when you open OpenHydroQual, it loads this plugin called main components, and I put some main components there. There's a catchment, there's a user, that thing is a user. You can always move your mouse on them and then you get a tooltip. So what it is a catchment, fixed head boundary, and now you're gonna have a fixed head boundary that is the head is actually changes with time. And then you have some links, and you have some sources. Of course, precipitation is one of them, and then some other things by default. Now, any other I can actually add plugins, and that will give me more of those, right? So when I add a plugin, it'll give me more of those. So basically, I can get one for, I don't know, open channel, I don't know, for soil, unsaturated soil, evapotranspiration, those things, right? By the way, just show you something. If you go to help and then click on this component description window, these are all the components that are currently, all the plugins that are currently loaded are components. So you have a catchment, and then you can see the description of all the properties, okay? I mean, slope, runoff coefficient, and so on. They actually have a name that may be different than the description, but the description is something that you see. What the engine sees is these names, which sometimes are different. And then you have some details, and then sometimes you have equations too. Now, in this case, for the catchment, I don't have that many equations, but I have here, for example, depth is defined as storage divided by area. Head is defined as elevation plus depth, plus water depth. Okay, does that make sense? Then you go to other things, I don't know. Chemical constituents, of course, a constituent. And then, you know, there are some equations and some descriptions of, for example, advect diffusive mass transfer, what equation is used. And you can always go change these things. Okay, you got to be careful with when you change them because, you know, sometimes they may not work. But anyways, okay, that is this. So now let's get started with building our model. So what I'm going to do is I can just add my catchment. Actually, here's what I'm going to do. Let's say you're interested to see how much peak flow reduction you'll get with a pond. Okay, so I'm going to actually make a pre-developed condition, and then in parallel, I'm going to also create a model that represents the system after the implementation of the pond, and then I want to do some comparison, right? So the first thing, I'm going to add this catchment. Actually, let me make the pre-developed first. So what I'm going to do is, by receiving water, as I said, I'm going to use a fixed head. So I added a fixed head, right? And then for the link, in this case, you got to know what kind of links to use the right equations. And if you look at, there's a manual that you can find all those things. But in this case, for the catchment, I'm going to use this thing called link from a catchment. Okay, it's just called link from the catchment. So I'm going to just drag this, connect it to my fixed head. That's it. I have the pre-developed model. It's a very simple model, just a catchment. Water runoff is generated. It goes to my receiving water that is represented as a fixed head, right? Then Then I'm gonna assign some properties to my catchment. So what I'm gonna do is I'm gonna extend these things so you can see the full names of the parameters. So what I have is, I think I said Manning roughness coefficient 0.035. Oh, I need a precipitation, so I need to take care of the precipitation. I'm going to come back to the precipitation. So I'm going to have a runoff coefficient. I said it's going to be 0.8. The slope in the direction of the flow is going to be 0.01. That's 1%, right? So you got to do the absolute value, not a percentage. The width of the catchment is, we said we wanted it to be 100 meters perpendicular to the flow, right? So basically, this is going to be 100 meters. You don't have to worry about all the properties, and I agree that makes sometimes things a little tricky. So there's an underscore height and underscore width. That's what it is, actually, the graphical width. So that's just the width of the icon that you see on the image. Sometimes actually it's handy to change them. People have created tools to create OpenHydroQual models, codes to actually automatically create OpenHydroQual model, and then you want it to graphically look nice and so on, so you can play with those things. So catchment area, we said 20,000. So I'm going to just put 20,000. At this time, I'm not interested in depression storage. Average water depth, just an initial average water depth on my catchment when I want to start the modeling. So it has to be called initial average water depth. I mean, we can assume it's 0, right? It hasn't been raining beforehand. Mean elevation of the catchment sometimes is important to do it, but I'm going to leave it at 0, right? So I'm going to say my catchment elevation is actually 0 at this point. Then I don't have any direct inflow onto my catchment. Loss coefficient is, don't worry about it, just a little advanced. And then you can always change the name, right? You can say imp catchment. Just change the name of your catchment to anything you want, right? Just put it, it assigns a default name, but you can change it to anything else you want. Or you can do, I don't know, impervious catchment 1 or something. Anyways. And then X and Y is just location. I can go change these things and it'll change the location that you see. It's not an actual location. It's just a location that you see on the screen, right? Okay, so that's what I have. Something I did not do was precipitation, right? So I'm going to do evapotranspiration later on. So precipitation. In order to get precipitation, we need to add a source, right? So you see here there's a source. Right now, we only have precipitation, right? So basically what I'm going to do is I'm going to click on that, and then I'm going to get a source, right? So it's called precipitation 1. By default, anything that you add, it's just going to be named automatically this way. It's going to be the name of the object, name of the class, and then a 1, right, in parentheses. Or the second one I create is going to be named 2 and 3 and 4 and so forth. But you can always go and change. I want to be just a little more relaxed. I'm just going to call it rain. How about that? Okay, so I'm just going to change the name of the source rain. Okay, fair enough. Then here's all I have to do. Oh yeah, I did the precipitation, but I didn't say what is my precipitation, where it should come from, right? Where should it come from? Okay, so now for precipitation, you need a data file. Let me show you the data file. I have 2 data files. Let me show you how they look like. By the way, I use, basically, you can create these data files using any text editor or Excel. You can create them with Excel and then export as a CSV. Let me go to where okay, here's LID conference data. This is the folder that I shared with you guys. So basically what I have is I have two files. Let me just show you one. I have this precipitation that represents LA County design storm, right? So that's a design storm that LA County uses. I think it's a 50 years design storm or something like that. So I'm just going to open it and show you how it works. So I'm going to open it. You can open it with Notepad. but I typically use this thing called Notepad++. Oops, I'm sorry, that's a PNG. Sorry, I opened the wrong one. I gotta do this one. Is it a CSV file? Yes. So it's a CSV file. You can actually open it with Excel too. So this is how it works. So look at this. It has too many digits, so it may be a little confusing. So basically it has three columns. The first column is, you can label them too. OpenHydroQual is not going to read your label. So it would have been wiser for me to actually put some labels to make things clear. This is very raw. But what it is the start time, the end time, how much it rained in between those time bins, okay? And they don't have to be uniform. They don't have to be structured, right? So you can have, I don't know, this much rain in this 1 hour, and then the next 2 hours, this much rain, and then this half hours after that, it rained this much. All you have to do, the start of that bin, end of that bin, how much cumulative rain you got during that. The unit can be anything you want, not anything you want. I'm going to show you what it can be. But here, this is for an older version where it had to be meters actually. How much it rained in meters. So this is actually the data that I have is how much it rained between the time events in meters, but you can actually do it with any other units.
Zeros here?
You can have zeros, yeah. Yes, you can have zeros. You can have zeros, yes.
Then you can just simply use the raw data that you get from
I'm going to actually replace this with a real data right after this, after the design storm, and then over there I'm going to have a bunch of rains. And exactly that's exactly the way you mentioned is exactly how I created it. You just download it from, I don't know, NOAA or any APIs that you use to download rain data, and then you need to do a little bit of reformatting in Excel. By the way, something. So the first column you see here it says my model, my design storm is going to start from time 0 and then goes for 1 day. So my start time is 0, my end time is 1, right? But in a lot of your cases, or a lot of real cases, your start time is not 0. Your start time may be January 1st, 2025, right? So you want to actually have an actual date. So in that case, have you seen that if you type a date in Excel and then change the format to number, you'll get a number? The numbers are going to be the same as that. So the numbers are going to be Excel numbers here. So I'm going to have something like 42,526. That may represent, I don't know, January 1st, 2025 or something like that. Does that make sense? And my next data file is going to be like that. So anyways, this is the design. So if you look at how it looks like, this is the design storm for LA County. This is how it looks like, okay? Sometimes, people use the cumulative version, but this is actually the non-cumulative one. So let's do that. So basically, now I'm going to go here. So if I say precipitation, just going to double click on this one. It says browse, right? Now, if you look here, here I can actually choose what unit my data file has. Okay, so if your data file unit is millimeters, the depths are in millimeters, you choose millimeters, inches, feet, right? But mine is actually in meters, so I'm going to keep it meters. And then I'm going to do, I said CSV, so I'm going to change this to CSV, and then have this LA County design storm. Just open it. That's it, I got it, right? So now I can actually I can right click on it and plot it. So this is what I have, right? And then in plotting, I can say, show it to me in, I don't know, millimeters, for example, or in inches or so forth. You can change the units and see the values in different units. Same thing, I didn't mention, same thing for our blocks. So look at this. When I said, for example, the width, there's a unit box here. So you can actually, if you want to go with feet or centimeters or inches, you can do that, right? So basically change your unit. Okay, so now we got everything set. I think I got everything set. I'm just going to save this as just stage 1. I don't want to lose basically, in order to run it, you have to save it. Okay, and then every time you run it, it's automatically saved. So basically, here's what I'm going to do now. I can just run it. So I have everything. I hope I have set everything up. So I just go and I'm going to go a little faster because I've been going really slowly. I want to cover a lot of material. So, but at the beginning, I want to give the introduction, and then I'm going to move a little faster. So basically, I just ran it for 1 day. Oh, I forgot one thing. I forgot one very important thing. I actually created the rain, but never applied it to my catchment, right? So basically here when you have the catchment, it says precipitation, and then I have to say what my precipitation is. And you can decide to apply precipitation to some components and not some other components, right? So basically, this is something that I forgot. So I'm going to actually, there's a drop-down menu. I'm going to pick my rain. So the rain is going to be applied to my catchment. Does that make sense? So I'm going to apply rain to my catchment, but I'm not going to apply rain to my fixed head, but I could, right? I mean, even though fixed head doesn't have a precipitation actually object. So anyways, so that's what we got. Let's see what we got. I hope everything worked out fine. So let's look at the precipitation. So that's the precipitation that I got. It's according to my, by the way, here the precipitation is cubic meters per day. So actually how much precipitation the 20,000 square meters received. So that's the total precipitation inflow, right? That my block received. This is total. It's not precipitation per surface area. Then I can do, I don't know, let's say the water depth, right? Average water depth, which I got something like this, right? So as I have the water depth is, the precipitation is more intense, I got a larger water depth on my catchment. It's in meters. You know, you may not want to see it in meters. It makes more sense to see it in centimeters or maybe inches. And this is how many inches peak sheet flow we get on the surface. You can look at the flow, right? So we get the flow. This is the flow. Now let's do cubic feet per second. So that's the flow in cubic feet per second that we get, and so forth, right? Okay, so we build our first model. Now what I want to do is that I want to add the pond to here, right? So I'm not gonna do everything from the scratch. I'm gonna actually use some of the things that I use because the properties of the catchment is, you know, the same, right? But I'm gonna keep this one. I'm gonna preserve this one too, right? So what I'm gonna do is that I will just make a copy of this, right? So that all the properties are also copied, right? So I'm gonna make a copy of this. Let me see how it's named. It's named catchment 1, so it goes to the defaulting, change it to something, or retrofitted catchment, let's say, for example. I don't know. You can call this, let's say, retrofitted catchment. There's no need to change the name, but if you want to. Okay, so that's, and then I got all the parameters copied, right? So I don't need to enter the parameters again, because it's the same from the same one. Now I need a pond, right? So basically, now I don't have a pond here. I don't have a pond block right there. So I need to bring in the plugin for the pond. So I'm going to go to Files, Preferences. There's an Add Plugin from the file. That's when you create a plugin and you just save it in a file and you want to use it. But if to add a default plugin, you just go to Add Plugins, and this window pops up. And then we have a bunch of plugins. Let me just walk you through them so you get an idea about what plugins we have. There's a pond. That's the one that I'm going to use. There are some evapotranspiration models. There's evaporation from surface water. So let's say you have, I don't know, you have a lake and you want to calculate how much evaporation happens from the surface of the lake. Groundwater, open channel, soil evapotranspiration models. These are evaporation that you apply to soil. And for the case of stormwater control measures, it makes a lot more sense to apply your evapotranspiration to the soil, not to the water ponding. Because the water ponding in a bioretention system is going to be very short-lived, right? It's just going to seep into the ground. And when you have water at the surface on a bioretention, it's usually when it's raining. So your air humidity is actually quite high. So not much evaporation happens during that time anyways. Most of the evapotranspiration happens actually from the soil later on. So anyways, so that's so we use this one. There's a pipe pump systems, rainfall runoff modeling, unsaturated soil, wells, water wells. OpenHydroQual has been used to model dry wells a lot in California, mainly Southern California and so on. Unconfined aquifer, mass transfer for things like chemical reaction, essentially reactors and chemical processes and so forth. Sewer systems, river processes, reservoir operation, build up and wash off. We're going to use this one when we talk about water quality today. And then some wastewater processes, and then plants. If you want to do plant, for example, uptake by plants and things like that explicitly. And now some of them are more developed, some of them are less developed, right? So some of them are mature, some of them are less mature. But anyways, these are all the plugins we have. Now what I'm going to do is that I'm going to just use the pond one. So just click on the pond. Okay, and then I got some additional, if you look, I got some additional components right here. So in front of the blocks, now I have a pond. It says a stormwater pond, right? I also got another one, aggregate zone. It's just that, you know, each plugin actually contains multiple components. It's not just one component. I mean, I call this a pond. It's usually used for BMPs and things that can be used for the ponding at the surface of a bioretention and things like that. But I also did an aggregate zone right there. Basically, I just put an aggregate zone here. I could actually put the aggregate zone maybe in some other plugins too. Maybe the pond was not the best one, but anyways, so that's what we got. And then we got some links as well. I don't know, you can have a drain pipe, for example, situation. We have aggregate layer to soil zone. Now we're gonna take care of soil later on, so we'll see how we use that one. And then there's a surface water to aggregate layer link. There's a soil to aggregate layer link. There's a wide channel. That's just a channel that is wide enough so that when we calculate the hydraulic radius, we can ignore the depth of water. We can ignore the wetted perimeter due to the contact between the water and the walls. Anyways, and then we have a weir. That's the one that I'm going to use. So basically, it's a weir based on power law rating curve. Okay. So that's what I got. So now what I'm going to do is that I'm going to add this pond. So now I have a pond between my fixed head and my catchment. And I'm going to just copy the fixed head too. Okay. I'll just connect them, and then I'll take care of the properties that I need to assign to the pond. So now the thing is that unfortunately we can't copy links. We can only copy blocks. Okay. So for links, I need to do it from the scribe. But there was no properties that we assigned to our link. You know, some links you assign properties to. In this case, it only has a name, right? So when I click on the link, it only has a name. So you can change the name if you want to, but no numerical properties. Okay. So basically, what I'm going to do is I'll just use the same link from the catchment, same link, to connect my catchment to, sometimes a little tricky, anyways, to my pond. Okay. And then I'm going to use a weir to connect my pond to the fixed head. Okay. So this is what it is. Then the precipitation is already there. It's in rain because I copied my catchment, so I don't need to assign the precipitation again. The same precipitation will go here. Here I need some properties for the pond. So let me go back to my PDF and see what was that. So basically, I'm going to use an alpha of 500, beta of 2, maximum operational depth of. I mean, anyways, that one we're not going to use. I mean, we can use it later on for the weir crest elevation, but anyways, I don't need the maximum operational depth. So basically, the alpha is 500 and then 2. So basically, here, if you look at the properties, there's this property called coefficient alpha in the rating curve. Okay. So this is going to be 500, and it's going to be 2, and I'm going to keep it that way. At the bottom elevation of the pond, let's make it, I don't know, maybe these are different than the way I did it in my, or in the slides and so on, but I'm going to just be realistic. Let's say the bottom elevation of the pond is 1.2 meters below the catchment, the mean elevation of the catchment. It really doesn't matter. It actually matters when I need to assign something so that I can basically do the crest elevation of the weir based on that. So I'm just going to do minus, let's say 1.2, right? So it's going to be the bottom elevation of my pond is 1.2 meters below the mean elevation of the catchment. Okay, so that takes care of the pond. That's all I need for the pond. I'm all set. Then what I'm going to do is here, let's assign the properties here. So let me go back to my PDF and see what I have for my weir. So what I have is the crest elevation is 1.2, and then the alpha is, this is something that I need to memorize. This is going to be easy. So 2.94 E5. Let me just put that in, and the rest I think is going to be, so basically my alpha, this is based on cubic meters per day. That's why the number comes so large. 2.94, I hope I memorized it correctly, E5, Okay, that's what I had. Then we said beta is 1.5, so I'm going to keep it 1.5 for a sharp crested weir or whatever that was. And then the crest elevation, I'm going to make it, look, the bottom elevation of here of the pond, I make it minus 1.2. Okay. The problem statement says that the crest elevation is 1.2, right? So relative to my bottom of the pond, the elevation of the crest is going to be 0. That was just a coincidence. I didn't mean for that to happen, right? In fact, it would have been nicer not to. Anyways, so does that make sense though? What I'm doing? So basically, the bottom elevation of a pond, I assume to datum is the pond is actually minus 1.2 based on my datum, and then the crest elevation of the weir is actually 1.2 meters above that, right? So the crest elevation is going to be 0. Does that make sense? Okay, so basically, let me go back and make this crest elevation here. I'm going to make this 0. It actually is 0 by default, so it's 0 already, right? By default, it's going to be 0, so I don't have to change it. So that's it. I'm going to save it. Now let's do it again, right? And then I'll pose a challenge. So that's what we got. So let's see what the effect of the pond was, right? So basically, this was my flow, the flow from the catchment, pre-developed catchment, right? I'm sorry, not pre-developed, pre-restoration, if you want to call it. So this was the pre-restoration hydrograph that I got. The post-restoration is going to be this. Does that make sense? You can, by the way, copy, paste. That's what we got. The gray, is that gray or green? The grayish green is the case for post-restoration. The purple is pre-restoration. Does that make sense? What you see? You see what is happening. So basically, the initial part of my storm was captured in the pond, okay, until the water level in the pond reached the 1.2 crest elevation, and then I have overflow after that, right? You can look at if you want to confirm that, let's just look at the water depth. That's the water depth, right? So basically, during my peak flow, it actually bumped up, but it took some time for the water depth to go up and get to the 1.2, and then that's it. So and then it stayed there, right? So now, what's the problem with this? If I want to model long term, if I want to do a long term simulation, you have to use the historic rain data, right? And I want to actually model the effect of the pond using long term data. Is there some problems? So what do you think will happen if I want to do long term? Just the same model, but I'm gonna apply a year, basically annual precipitation. Let's do it and see what happens, right? But can someone guess what's gonna happen? It's gonna be, let me tell you what, it's gonna be a very boring answer. It's not gonna be exciting at all. That's exactly true. I don't have any way to, I don't have a drainage. So basically the first rain is gonna fill up the pond, right? And then it's going to be just to stay there. From that point on, any water that comes in is going to overflow right away. Okay, perfect answer. So let me, but let's do it. So what I'm going to do now is, all I'm going to do is that I will just replace my rain with another rain data that I had. That's actually from Baltimore. Actually, I downloaded it from Baltimore airport station. It's called sample rain data. I call it sample rain data, okay? But if you look, I'm just gonna let you glance through the data. So that's what it is. If you look, it starts from 40,179, and then goes to 40,000, I don't know, 179.02, right? That's 40,179. If you import this into Excel and then change the format to a date, it's a date. I think we're gonna find out what date that is. I don't have on top of my head, but it's a date, right? Anyway, so let's do that. So basically what I'm going to do now is I'm just going to go to my precipitation. I'm going to keep the same thing, right? By the way, anyways, let's just do it. So that's my rain, right? So now what I'm going to do is I'm going to click here. Let me expand this, maybe shrink this a little bit so you can see what I'm doing. So basically, I'm going to click on this, right? And then go and get sample rain data. That's my sample rain data, right? So I'm going to actually choose this one. The unit is again meters, okay? So the unit of depth is meters, which is a little weird because the numbers comes off to be too small. But anyways, if you want to look at this rain data, just right click on it, plot. So this is how the rain data looks like. It's actually 3 years of data from January 2010 to December 2012. So 3 years of data, okay? So I'm gonna do the simulation over 3 days. I don't need to change anything except for one thing. By default, we never said what time duration OpenHydroQual has to run. Basically, it just automatically did it for 1 day. By default, it does it from time 0 to time 1, or day 0 to day 1, right? It's 1 day. But then if I want to do it for a specific period of time, I need to indicate that. I never did that, right? So let's do it. So what I'm going to do is that I'll go here. So settings. If you go to settings, general settings, okay. Then you have a simulation end time and a simulation start time. By the way, there are some criteria. Properties have some criteria. Sometimes you may enter a number and OpenHydroQual is not going to accept it. The GUI is not going to accept it. Because I don't know, for example, if you want to enter hydraulic conductivity and you enter a negative number, it's not going to accept it, right? Or the Manning roughness coefficient, if it's 0, if you enter 0, it's going to give you a message and say this is not a valid number. So the dates, the criteria is that the end date has to be larger than the start date, which is an obvious thing. But in order to do that, I better actually first set the end date and then start date, because probably it's going to pick on me if it may be fine, but if it's going to pick on me if I say some number here. But anyways, I'm going to do, what was that, 2010, right? So basically my data was started at 2010, right? It's just, that's a bug. Basically, if I say January 1st, 2010, it does some sort of, I don't know, 11:59 p.m. of the day before, and then it goes to December, 1 day before. But anyways, then, you know what? I'm not gonna do 3 years. I'm gonna just do 1 year, so things go more quicker, right? I mean, it's not gonna make that much of a difference, but no reason to simulate 3 years. I'm just gonna simulate 1 year. 3 years is gonna be the same thing, right? So basically, let's do 2011. Good. Again, same thing happens. Oh, I'm sorry, I made a mistake. This has to be, by the way, it didn't pick on me. So this has to be 2011, right? So basically, it's gonna be, yeah. So 2010 to 20. I mean, you know what? I just messed up. Anyways, I'm modeling 2011, right? I got a little confused with. So I'm going to model this period of time. We had rain data for that time. Anyways, good. Ready? Go. Yes, go ahead.
Set your start time before your data started.
It's going to just assume no rain. Yeah. Done. By the way, you see these things happening. You see these bars and so on. There's just a computational time step, because OpenHydroQual uses an adaptive time step. So basically, it just tries to maximize time step to an extent where the model is stable, right? So I just maximized it, and it's dynamically adjusted. So if you have, I don't know, if you want to model an LID for most of the year, not much happens, right? When you don't have rain and things like that, it's just dry. Not much happens. When not much is happening, it can actually use a larger time step. And then when you have a rain event and you want more detail, it's going to use the smaller time steps, right? So that's what you see. Anyways, it's done. When it's done, it says all tasks finished. So these are very simple models. I've run models using OpenHydroQual that are much more complex. And if you want to do a year, you got to just wait some time, 20 minutes, 30 minutes, 1 day, a few days, all possible, depending on the complexity of your model. Okay, so that's what we got. I'm sorry, forgot your name. Kyle. So let's see Kyle's theory. So So this is what happens. If you look at this, the flow, this is the flow rate that I got for with the post restoration case. Let's do it for the pre-restoration. Okay. So that's what I got, right? So let's now compare them to each other. So I'm going to copy this, paste it here, and see what happens. Okay, that's what I got, right? Look at this. Maybe I got some differences at the beginning, even though it's not very easy to see. But if I look at here, maybe the first event, I got some difference. Maybe not. But anyways, zoom extend. But the rest of it is actually pretty much the same, right? That's exactly because of what Kyle mentioned, right? So basically, the water is not draining, right? The pond is actually holding the water. So if I want to make it more realistic, I need to somehow get rid of the water that is in the pond in between the events, like through infiltration, through an underdrain, evapotranspiration, something like that. Okay, does that make sense? So so let's do this. So what do you want to do? Let's do this. I'm going to actually turn this into a, it's actually very embarrassing. I don't know, detention and retention. Anyways, so turn it into the other one, right? The retention pond. So I'm going to actually add an underdrain and let the water to drain out in between the events, right? So so now here's the problem. Effectively, in order to do that, I'm going to need to connect my pond to this fixed head twice, okay? Because one is going to be the weir, right? The other one is going to be the underdrain pipe. They both start from the same pond and then they end at the same fixed head. So I basically need a trick. So what I'm going to do is that I'll need to. I mean, by the way, OpenHydroQual does not allow me to do that. So you can actually connect two blocks with two links. So between each two blocks, there has to be only one link, right? So I'm going to trick the system. I'm going to actually add a junction, some sort of a node. Let's do this. I'm going to actually add something. I'm going to add a catch basin, right? I'm going to add a catch basin and say the pond, the water from the pond underdrains to the catch basin, and then it goes to my sewer, right? In reality, probably you have something like that, right? So, or you can do other things too. But anyways, so what I'm going to do is that in order to get the catch basin, let me see what I'm going to do. I'm going to add a new plugin, okay? So the catch basin is actually in this plugin called Sewer System, right? So I'm going to get the sewer system. I'm going to add it. So now I got a bunch of other components, but a bunch of additional components. So I got this, you have a sewer channel segment, for example, and then we got a bunch of links, sewer pipe, and so forth, right? So what I'm going to do is that I'm going to use a sewer pipe, by the way. So let's do this one. Let me add a catch basin. So I'm going to add a catch basin. What a catch basin is just a box. So you have a box, it has an area, you have a pipe going into it, and the pipe goes out of it, right? And then the flow, that it controls the head, right? Depending on how much storage we have, right? So what I'm going to do is let's just add one. So I'm going to add this catch basin, and I'm going to make it small because it's a minor thing, or maybe in reality also small, anyways, but it doesn't matter. Then what I'm going to do is let's use I mean, I can do several things. For the under drain, I can actually use this drain pipe. It uses the minor loss coefficient, like K times V squared over 2G, if you remember from your fluid mechanics course. And the K is the minor loss coefficient. But I'm going to use just a sewer pipe, right? Which uses Manning's equation. So basically, let's say I have a sewer pipe here. And then I have another sewer pipe connecting my, no, it's easier with the mouse. Okay, so I got it. So now basically what I have is that my pond goes to catchment, goes to my fixed head. I need to do some, make some decisions about the head, because for the weir, it didn't matter what the head of my fixed head is, right? It didn't matter. It just uses the upstream. For the weir, it only uses upstream, basically head to calculate the flow rate. But for a pipe, it actually uses a downstream head and an upstream head, right? So I got to be careful what to assign. So what I'm doing is I have to assign some realistic numbers. So the bottom elevation of my pond is 1.2. Okay, so I want to make sure the bottom elevation of my catch basin is actually below that, right? So that water flows to the catch basin, right? So I'm going to do, let's say, I don't know. I mean, by the way, I need to do a base area. So that's the area of my catch basin. So let's say this is one square meters. And the bottom elevation, I'm just going to go below the pond. So I'm going to do, the pond was minus 1.2. This one I'm going to do minus 1.3. Of course, in your cases, you're actually, I'm just creating fictional systems. In your cases, you should have that information, right? Because you're actually modeling real systems. Yes.
So I got a question. So if you set the fixed head higher than the weir,
it will flow back. Yeah, it will flow back through my pipe, not through weir. The weir is, the equation is so that it just gives you the flow based on the upstream water depth. But for the sewer pipes, it'll flow back, so you get a negative flow. So I want to prevent that. So that's why I'm assigning the right. So anyways, for the fixed head, I also have to do that. So there's a head. You see the head? That's my fixed head. That's the head. So I'm going to make sure it's actually lower. So let's make it, I don't know, minus 1.5, for example. In my slides, it may be different, but I just don't want to go back to my slides and see what I assigned over there. I'm going to take a little bit of risk. So anyways, that's what I have. It's just every once in a while I like to save it. And then I need to assign some properties to my pipes, by the way. So these are the pipes. These are sewer sewer pipes. Let's see what we have for the sewer pipes. You know what? Maybe I have something. Yeah, this is what I have. So I'm going to actually use this one. So let's say it's a 4-inch pipe. Okay, so I'm going to assume it's a 4-inch pipe. Invert elevation of pond is 0.1. So actually, I can go up. I can say my pipe is not necessarily, doesn't start from the bottom of my pond. It actually starts from a little above that. So it's going to start from, let's say, for example, 0.1 above the bottom of my pond, right? Then the pipe length is 50. The Manning roughness is 0.013, and so forth. So let's do that. So using some of these and not all, not very disciplined. So the Manning roughness we said is 0.013. The diameter is 4 inches, which is, actually I'm going to make it 4 inches. How about that? So just a 4 inches, right? So this is going to be inch. The start elevation, my pond bottom elevation was minus 1.2. So this one I'm going to make it minus 1.1, right? Minus 1.1. It could be minus 1.2 as well. So it's exactly at the bottom of the pond, but that's not very realistic, right? But this way, some water will always stay in my pond, cannot be drained, right? Because the pipe is a little higher. The pipe length, I said 50 meters. I'm going to do 25 here, 25 here, right? You can do it any way you want, but the most rational way may be to do 25 meters here and then 25 meters over there. Then the end elevation, that's where the pipe ends, okay, at the catch basin where it ends. I said the bottom elevation of my catchment is minus 1.3. So how about saying that the pipe comes in 10 centimeters above the bottom of my catch basin? So let's say minus 1.2. And anytime anything that I'm saying doesn't make sense, it's not completely clear, please feel free to stop me and ask me to clarify. Oh, that's the start elevation. So my bad. So this has to be 1.1. It's actually alphabetically ordered. The properties are alphabetically ordered, so it's not always very. So and then very rational. So basically, end elevation is a minus 1.2. Then I'm going to do this one. Same thing. Diameter is going to be 4 inch. Okay. The end elevation is going to be, the fixed head we said is what? Minus 1.5. So let's say this is minus 1.52. Okay. Minus 1.5. The pipe length we said is 25. Oops. It says, this is the error that I got. So I didn't enter the length, and it says you're not allowed to enter the length that is 0. So I have to, if I run it, it's not going to run. So basically I'm going to 25, and then the start elevation is going to be, what was that? Minus, let's say 1.25, for example. That's still above the bottom of the catch basin. Is that the geometry is clear? All good. So let's do it. Now I'm going to do the sure. It's sewer systems. Yeah. Yes. I could do it in metric too, but if I want to do it 4 inches in metric, I'm going to need to do a quick calculation. Just multiply that by, I think, 2.54 or something. Yeah, but it doesn't have to be. You can do it with any unit system you want. Okay, good, all good. Let's see what happens. Just going to run it. Oh yeah, I got an error. The error in the value is assigned. What it says, by the way, this log window is actually a good thing. You can see, what is basically it's something. So it says in object, catch basin want to fix it to Manning roughness coefficient must be greater than 0, right? So basically that the reason for this is, just gonna move this, just close it. It pops up when needed. So Manning roughness coefficient, I completely forgot about that, right? So basically I need to assign a non-zero value, right? So basically I'm just gonna do 0.013, okay? So now all good. Where's my mouse? Okay, here you go. Save, run. Okay, done. Now let's see what we get. So this is the pre-restoration, pre-implementation or whatever. This is that. Then I have, by the way, I have a overflow. This is my overflow. It never happened actually. It only happened once, right? Only once the rain was intense enough to fill up the whole pond and overflows, right? But if you look at the underdrain, you should have continuous underdrain. So basically, this is my overflow, and then this is my flow. You get a bunch of things, by the way. You get a bunch of information for the sewer pipes, area, start area, end area, hydraulic gradient, effective hydraulic radius, wetted perimeter, and those things. Most of them you don't care about, right, in practice. But if you want to actually debug, you want to make sure that the calculations are correct or something. So basically you do flow rates. Now that's the flow rate we got. So this is the flow rate we got. Let's compare the flow rate for the underdrain. The overflow only happens once, right? So let's just ignore that. And then I'm going to copy this, maybe paste it with my previous retrofit, and this is what you get, right? So look at it. How much we affected the peak flow? Quite substantially. The colors are kind of close, but you see that the magenta is the underdrain for the case with stormwater control measure, and then the brown is the pre-retrofit. Okay. Any questions?